Hello, students. So the next topic we're going to cover in class is actually one of my favorite topics. It's called approximate integration. And this will be a topic where, like the name suggests, we're just approximating the value of a definite integral. So remember, what this really tells us is we have some function, and what we're interested in is really the area under that function between some starting lower bound, and then some ending upper bound. So we're really just interested in what this area is of this function between a and b. And now we've already developed a whole lot of integration techniques to try and help us actually compute these types of ideas in terms of computing integrals using, partial fractions, integration by parts, trig sub, and so on. The distinction with what we're doing today is we're really kind of assuming that these functions are too hard to integrate. Really, this means is that there is no known antiderivative. So it's not just that they're too hard to integrate, it's the fact that no antiderivative is known to exist for some of these integrands. So for example, like a function, if we're considering what is the area between 0 and 1 for this function e to the minus x squared. There's no known antiderivative. So what we're thinking about today is, well, if we still want to figure out what the area under a curve is for some of these functions, and we can't directly compute an antiderivative, what's our next best option? And this is where the idea of approximate integration comes from. So we're going to be revisiting a lot of ideas today. So for example, ideas like Riemann sums. We started basically putting rectangles under curves and adding up the area of a bunch of rectangles to give us an approximation under the curve. We're going to continue in that same exact vein, except instead of just using rectangles, we could introduce other shapes as well. So things like trapezoids, which will lead us to the trapezoid rule for computing areas under curves. And now, since these are all going to be approximations for us, all these approximations inherently come with what we call error bounds, because we're not exactly finding the area under a curve in general. We're just approximating its value. So the last thing we'll try to determine is the error bounds associated with a particular kind of integral approximation. And as we'll see in class, these error bounds will depend on a number of different things. The particular function we're trying to integrate, the integration bound. So like, what is A, what is B, for example, or the kind of integration approximation we're using. Are we using rectangles? Are we using trapezoids? Or it could just be the number of partitions that we're subdividing that area into. So the next video, I'll do a basic example with how we can compute the area under a curve using trapezoids.